is here. Very thin streams of lava that are usually created in natural eruptions. If the lava falls over an edge or gets caught by strong winds, these are very difficult to find because these strings are made of volcanic glass, so they are very fragile. They will break apart very quickly after forming. In Icelandic, we call them Nornahaug, which translates to witches here. And as soon as the lava starts flowing into the room, it begins to release the heat very quickly, and you can see how the lava is cooling down, because the more heat it releases, the darker the lava appears. And already in this area, it looks like the lava has stopped flowing, but further down you see more lava still accumulating. So what's happened here is that the lava on the surface has already cooled down enough to form a solid crust. And lava is a very good insulator. So this thin crust on the surface insulates the lava in the middle of the channel, keeping it hot molten liquid. So there is still lava flowing through here and accumulating further down. In natural eruptions, lava tends to lose around 100 degrees Celsius for every kilometer it's flowing. But if it flows through its own insulation, for example lava tunnels, then it only loses 1 degree Celsius per kilometer. So by insulating itself, lava can flow much further before it cools down and becomes solid. I've also brought with me some ice to show you what happens if we cool down the lava very quickly. Because if you cool it very quickly, it's not able to crystallize into rocks, so instead it becomes what it's most made of. And this basalt lava is around 47% silica. So when we put ice on it, it transforms into volcanic glass. You also see the lava rising up very quickly. This is actually the steam from the ice that's pushing into the lava and inflating it. That can also happen in natural eruptions from gases like sulfur dioxide and carbon dioxide. These gases can inflate molten lava and create lava caves. And you see the surface is transforming into this beautiful black and shiny volcanic glass. Just cleaning the lava a little bit here. So now this is completely solid. And also if you go a bit higher, you have a very solid surface, but it could still be liquid inside. So I can actually go under the lava and begin to lift it up. And it holds together, but then it will start opening up. And we see this liquid come out. It's not as liquid as when it enters the room, because as the lava is cooling, it gradually becomes thicker and more viscous before it finally solidifies completely. So now we have a very thick and viscous type of lava here. That's a pretty fun job. Play with lava every day. Warmer than the glacier. And also, you can see this little bubble we got down there. You notice that the glass here in the bubble, it is actually transparent, and that's because it's very thin. Once the glass gets thicker, it turns black because it also contains other things than silica. This lava is also rich in iron and aluminum, titanium and magnesium, which gives it this black color. But yeah, this bubble, this glass is very, very thin. If we just touch it very gently, it breaks quickly. Very fragile. And of course the lava is still very, very hot. If you just put a little piece of paper, it will instantly start burning. Then we get the lava lamp. Feel free to bring out any marshmallows if you want to make some s'mores. And also we are able to hear the sound of the lava cooling right now. If you listen to it, you'll hear these little crackling sounds and popping sounds. What's happening now as the lava is cooling, it also begins to take up less and less volume. So the lava is shrinking. And as it shrinks, it transforms from liquid to solid, so it begins to pressurize itself, and then it starts to fracture and break up into smaller pieces. So that's the sounds we are hearing from the lava. It's cooling, shrinking, and breaking. And also in this area, you see we get these patterns forming on the surface that looks a bit like the lava has been wrinkled up. And this is actually a common lava formation to see here in Iceland. So these patterns in the lava are called Ropi Pahoihoi patterns, another Hawaiian name. And what happens to make these ripples is that the surface layer cooled down very quickly because it's exposed to the atmosphere. So then it became thick and viscous. And while that was happening, more liquid lava was still pouring in from behind, and it started to push the viscous lava out towards the edges, causing it to compress slightly and create ripples on the surface. And as the lava is now cooling, we can try to break it. So let's see if we can break off a chunk. Yeah, so now it has solidified, and you can see here the lava is perfectly cooked, medium rare. Here I cannot yet break it because it's still a little bit liquid inside. On the edges it cools a lot quicker. And we are going to see that all of this lava will turn into volcanic glass, not just where I put the ice. And the reason for that is that we only have about 70 kilograms of lava here in total, which is very little compared to natural eruptions. So that means that basically it cools down too quickly to crystallize. But if we had a lot more lava and it took months and years to cool down, then what happens differently is that the molecules in the lava have enough time to move around and organize themselves into crystalline structures. And if that happens, we get these rocks you see here around the slide. So these rocks are also basalt lava. They are chemically exactly the same as this. They just came from a much bigger volume of lava that cooled down slowly enough for the process of crystallization to take place. And here as well now it's solidifying. We can break it up a little bit. And we are seeing now the lava has been getting pretty dark, but it's still glowing a little bit here and there. But when it enters the room at 1100 degrees, it is very bright. And all the light that you see coming out of the lava is due to the massive amounts of energy that we put into it to bring it up to these temperatures. So to make lava ready for a lava show, we have to start the furnace at least 5 hours earlier. And during those 5 hours in the furnace, we are basically accelerating how quickly the molecules are moving in the lava. So they go faster and faster, and as they move, they produce friction, which gives light. And now that this energy is releasing into the room and heating us up, that means the molecules are now slowing down, and therefore the lava gets darker. And just by looking at it, you can tell how hot it is. Anywhere that's completely black, this lava has already cooled down below 600 degrees Celsius. But if it's still glowing orange, like it still is inside here, then it is still above 600 degrees. So right around 600 is when the lava stops glowing. And in this case, it turns into this beautiful black volcanic glass. And we did actually test once how long it would take for this lava to cool down to room temperature. Mostly because we had nothing better to do during the COVID pandemic, so we were experimenting a little bit. So we just poured the lava into an empty room and let it sit without breaking it. And up here in the thick parts of the channel, it took actually up to 3 days before it reached room temperature. So even though it's only about 70 kilos, it still takes a lot of time to cool down. You see, it's still liquid in the middle of this area. Excellent. And now I have a question for you guys as well. I wanted to know if you guys would like